Again, my apologies for being out. It's not ideal, but I'll be back on Monday and we can tie up any loose ends around these topics of the atom and the periodic table and trends in the periodic table and the flame test. But I hope you were able to make a good stab at some of those questions from yesterday. I'll have some time to finish those today in class as well. Well worth doing. I was just having a look. I know we haven't really used the book an awful lot yet because I kind of have the notes done, but I was just looking at the actual book. So this is the contents page of Chemistry Live, right? So if you say, well, chapter 1 is nothing really, it's just like the introduction to the book. And then it goes up as far as, so the whole course over the 2 years is 24 chapters down here on the right. So, I mean, if you take all the chapters then, being the 2-year course, there's 23 chapters in the book, and look what we've done so far. So if we go back to this page here, we've already covered chapter 2. That's all Thomson and the plum pudding model and the properties of subatomic particles, like a proton is +1 and an electron is -1. We've done all this. We've done the electron of the atom. So we've done Bohr's and we've done Neil Bohr. And today's lesson is going to be on this guy here, atomic absorption spectrometry. It's this last little bit that I want to go through, but it's also 1s2, 2s2, all that stuff we've done. We've done the periodic table. So we've done chapter 2, chapter 3, chapter 4. So that's 3 chapters out of 23. And we've also done chapter 7, which is trends in the periodic table. And the questions you were doing today and yesterday are based on these 4 chapters. So not bad. We're at the 23rd of September and we've already covered 4 chapters out of 23 of the 2-year course, which is good going if we know it. So we're going to take our time. We're going to do another little small thing today. We'll give you more time to try those questions, those exam questions that I gave you yesterday. We'll tie all the loose ends up and go through any issues that we're having and any bits that need to be done, because this is a guaranteed 1 question, if not 2 questions out of 8 in Leaving Cert higher level chemistry. So if we can get this under the belt now, even if it takes us another week or 2, it's worth doing, and it gives us plenty of time, and we're well on track still to finish the course by mock time in 6th year to leave us loads of revision time. Okay, so we'll get back to it next week. For today, there's one little small thing I want to do with you. And this is in the Schoology group. I just pasted it here into a OneNote group just so I could write on the screen. In this OneNote page, and you're all members of this as well, so but the notes will still go up on Schoology. Just out on the right here, so this is called, what did I call this group? It's in the same folder under the periodic table, the only folder we have there. So there's the one from the last day, and here's the atomic structure one, and this is in the Schoology, as I said, right? Out here at the right, just in case there's still any confusion, here is all the 1s2, 2s2, 2p6 business that we were talking about. So there are all the energy levels drawn out for all of the elements that you could possibly need to know, and the ones that are the kind of don't obey the rule totally are these ones here. There's 1 and there's 2. Remember, if this 3D sublevel is half full or completely full, the electron jumps up to it. So that's why you have the 4s1 in both of those, and 3d5, 3d10. Okay, and any questions on this? Again, I know I sent you a video yesterday, but I can draw them all out on the board and show you how the arrows work and all that the next day if anyone is still finding that confusing. Right, this is the other bit. You'll see there that this is atomic structure, and it is only higher level. So it's a bit that they only ask in the higher level paper. So they don't ask this in ordinary level. And it's kind of based around the flame tests. And it's all well and good us knowing that the flame tests are give you the different colours, but I suppose why does one of them go pink and one of them go blue and one of them go yellow and orange and stuff like that? So this bit kind of explains it, and this is available in your Schoology. Okay, so this guy again, Niels Bohr, what he was doing, he was passing light. You know where you pass, if you pass light through water, it kind of turns into a rainbow. It's kind of that kind of thing, right? So he passed white light through a prism. We did this in junior cert physics, and what you got was a continuous spectrum, like you see in a rainbow, all the different colours. But Bohr then passed light from a hydrogen gas discharge tube through a prism, and you got a different one, an emission spectrum. So you have two. You have a continuous spectrum, basically there's no gaps in it, and an emission spectrum. I'll just flick down and show you the difference between the two of them. There they are there. So in your continuous spectrum, you see you have all the colours fitted in, there's no gaps. And an emission spectrum is this one here. It's mostly black and you have the lines in it. That's the difference between the two. That's what Niels Bohr did. Here's what we found. So I know we didn't actually find this. We kind of didn't get potassium. Remember this? Remember the potassium? I was going on about lilac and it was coming out as yellow. Now we're going to do that one again. The rest of them kind of panned out. But I think what we were seeing there, because remember some of you were seeing the yellow, but there was a bit of blue in the middle. So I think what we were actually seeing there was a wooden taper burning. So we were seeing actually wood burns yellow, but potassium burns lilac. So what we'll do is we'll redo that, but instead of using the wooden splint like they suggest here, like we used, we'd throw it on a needle and see do we get that lilac colour. I think that was the issue at the time. The wooden tapers weren't damp enough, and we're actually just seeing burning wood as opposed to burning potassium. But there's our colours. We have the 6 flame tests. They're the 6 salts that we tested, and there's the colour. But the problem, I suppose, where you have to go next is why. Why do you get those? So a couple of definitions. You have a definition for an energy level. So that's the energy that an electron has, the amount of energy that an electron has. So the ground state of an atom this time is where the electrons occupy the lowest available energy level. So remember when we were drawing these energy levels, they had these boxes. Oops, use this. You had these boxes, 3 boxes. And what you saw was arrow went in, arrow went in, arrow went in, and then arrow went in, arrow went in, arrow went in, before they jump up here. So there was nothing filled up here until all of these energy levels were full. That's what it means in the ground state. When you excite something, great way of exciting something in chemistry. So the excited state is where the electrons occupy higher energy level than those available in its ground state. A great way to excite something is to, well, like we did, set the thing on fire. Hold it over a Bunsen burner and set it on fire. And then the electrons will occupy higher energy levels. It's not going to give us any colour, but they'll jump up the higher level. So here's the kind of step-by-step method of how we saw flame tests. So in the ground state, the electrons occupy the lowest energy level, like the way we draw them. And when you add energy, they jump. They jump to a higher energy level. And then they're excited. But as soon as they get up to that higher energy level, they fall back down. And when they fall back down, they give off energy as a photon, which we can see. So each frequency appears as a coloured line on the spectrum. So it appears as a colour. So it appears as a colour to our naked eye, like lilac and yellow and blue and red and all those kind of things. But if you were to put it as a spectrum, or if you had like computer to monitor the different colours, what you would get is something like this, a continuous spectrum. Now, the technology you need for that is atomic absorption spectroscopy, and you need an AAS machine, which are a couple of $100,000 each, so we're not going to be getting to it anytime soon. But the principle of that, so if you were to actually measure the flame tests, white light is passed through a sample of the element. So you pass a white light through any sort of element. That gives us an atomic absorption spectrum. And the dark lines correspond to the coloured lines in the emission spectrum. So if we look at the emission spectrum over here, so emission spectrum, and here we have a green line there, and that will correspond to here. The blue line will correspond to blue, purple will correspond to purple, red will correspond to red, and so on. Okay, so you'll use it for things like looking for certain elements dissolved in water. So if they're going down to a beach and they're saying, is there too much lead in this water? Is there too much something in this water? What they'll do is the atomic absorption will allow you to look how much of a particular element is in the water. Okay. Pretty much the last thing, lads. A sub-level is division of the main energy level. So we've done the sub-levels already. You have the S sub-level, SP, SPD. So you remember, if you think of how many electrons they can all hold, the S1 holds 2, the P1 holds 6, and the D1 holds 10. Definition: Heisenberg uncertainty principle. It's impossible to measure the velocity and speed of an electron simultaneously. So they're so small, they're moving so quick in different directions, it's pretty much impossible to measure the velocity and speed. Remember, velocity is speed in a particular direction. All right. And the very last thing is the limitations of Bohr. So we kind of go through what Bohr did, and he looked at the energy levels, and he kind of come up with the emission spectrum, absorption spectrum. But Bohr only looked at the emission spectrum of hydrogen. He didn't take the wave nature into account, so how electrons travel, and he didn't take the existence of sublevels into account. So if you have a look at this one here, so this ball, it kind of looks like a ball, but that's the path of the electron. So the electron's going around like that, around in a circle. So electrons traveling from say in a clockwise direction. These ones here are your P sublevels. So this is in the figure of 8. So your electron is traveling like that, across around like so, like that. So it's traveling in like a figure of 8. So you have 2 electrons in here, 2 electrons in here, and 2 electrons in here, because you know that P holds 6, S only holds 2, and D, which is not going to be needed, is going to be 10. So S, P, and D. So your shape of your orbitals, and I put the full table in for you there. Okay, yeah, I know there's a lot in that, right? So what I want you to do for the rest of today's lesson is go back to those periodic table questions, and there'll be 1 or 2 that you'll be able to answer around, in particular, this here, atomic absorption spectrometry. And I've added in an extra question for you in the Schoology group that you can give it, that you can add to the set of questions and give it a try. It's a quick 10-minute job, and that, for all intents and purposes, finishes us on notes for those chapters on the atom and the periodic table and trends in the periodic table. But we will give it, as I said, another week or so to tidy it up, because it's important you know it is a definite question, if not 2 full questions out of 8. So we'll give it the time it needs and correct the questions fully and revise over all those different characters who invented the proton and the electron and the different models and the cathode rays and so on and so forth over the next week. Okay, right, mind yourselves, and I'll talk to you on Monday.